So we just heard about a deployment of open networking hardware, and open networking hardware can be used in many ways. And Thomas Elkund is going to talk to us about how Kaloom makes software-defined networks with open hardware.
Can you hear me? Yes, I will. Thank you. So I come from a small new company called Kaloom, and we are doing software-defined fabric for the data center. And it was almost like the previous speaker was helping me to teeing up what our founders came together to create when we created Kaloom. So the founders have 20 years experience of building products and managing data centers. And we wanted to build the most scalable, fully automated, at lowest cost data centers. So we have had a lot of challenges in the past with different networking gears. So previous speaker has been talking about automation, and we agree. You know, there is a lot of problems in the underlay, how you manage the cables, how you put it together. You know, typically where you have most of the problems are with different spanning tree related protocols. So we have fully automated that away completely. You know, programmability, we believe it's important. As you can see, you know, people try to unify the server and the storage architecture where the DevOps has been very strong. So you have been bringing developer-centric development for innovation, but it's been lacking in the networking gear. So we believe a lot of the same principle is valid for networking, and that's why we are treating networking exactly as a server node or a storage node. And you will see that in a few examples here how we're done. We also believe once you do that, that programmability is important. So, you know, like the previous speaker talked about network DevOps, but what's the point if the gear is not programmable? Scalability, it's super important. We learned that from the hyperscale guys that has been very successful, you know, which means that you need to simplify individual nodes to reach a new level of scalability. But it also means, you know, scaling all the virtual components and the infrastructure components you have in the data center. And you will see some of the thinking there, what we have been thinking about. And we also believe that key here is to leverage white boxes. So automation drives down the OPEX and white boxes drive down the CapEx leg for data center networking, of course. Open networking, as the previous speaker have been talking about, we believe are heavy in that. We've been seeing that, you know, how do you create not only open APIs, but how do you leverage open source component? How do you integrate and help to contribute back to the community in Kubernetes, in Linux, and in other forums. Latency is becoming a problem for different type of workloads. So how do you get around and have a better solution for that? We've been putting some thought into the end-to-end latency. That goes not only into the switches itself, it also goes into the I/O between the switches and the backend servers and storage nodes. You know, a data center operator today, he may have many tenants. So how do you host those tenants in a fully isolated way, all the way in an end-to-end fashion? You know, we have been looking at how we introduce network slicing to come around with that. And, you know, the existing solution out there today is very insecure, because if you have different existing mechanisms. Let's say you have a VLAN-like protocol, and you can put up a port sniffer on another VLAN, and you can see the other tenant's traffic. We believe that's not good enough, and no new techniques are needed to better isolate the different tenants' traffic. Of course, IPv6 is needed. We believe everyone talks about hyperscale, scale you know, to the moon. So of course we need to be prepared to have IPv6 integrated from day one. Also, the resource inefficiency. So when you look at this and start using, you know, improving the I/O between the networking gear and the backend server gear, how do you also improve the latency, the throughput, and how do you reduce the resources involved in doing that processing? So all of these requirements are some of the key requirements that the founding team thought needed a new fresh look at when they designed Kaloom. Open networking, I mean, this is sort of one of the leading industry forums that drives open architecture, both on the hardware side and the software side. And we believe in that core principles. You know, standard Linux base, like the previous speaker here talked about, you know, you have servers and storage node that you've been using. You have that both for your network application as well as for your normal application, like CRM system or whatever it might be. They need to be treated as the same. So we believe that all the networking gear should be seen exactly as a server node, which means that you don't need specific kernel patches or anything with this proprietary networking operating system. The difficulty that you have with that is, for instance, if there is a security patch in Linux, if you have a patch kernel, it can take 6 to 12 months before that is fixed in a network operating system. But if you're using standard Linux and a normal DevOps flow, a CI/CD flow, it's fixed in days. Those benefits you get for free. So we believe those are very strong fundamentals behind that. Open API, of course, you're not alone when you build a data center. It's an ecosystem around you. And we believe that this openness, all the way down from open hardware to open APIs to open source components, make it simpler to have a fully working interoperable solution for the data center. So and I will talk about that a little bit in a few slides, we believe also very much in open source. So we work very strategically today with Red Hat, and we have a lot of cooperation in improving networking, for instance, in Kubernetes. So we've done major improvements with the CNI interface there. Main improvements we have done is to improve for mission critical applications. Because like the previous speaker talked about also, there is typically a disconnect with the application developer and the networking developer. And sometimes you have networking related problem, which is, difficult to understand when you have an application development background. And we try to bring those two worlds together. And another fundamental approach, of course, is when you do open networking, you're thriving to have no vendor lock-in. You always want to have multi-vendor deployment. Okay, so on the networking hardware, people have been talking about disaggregation. Disaggregation comes in at multiple levels. On the highest level is to separate the appliance model and separate hardware from software. The hardware itself is waiting to be disaggregated over time, which will need more complicated equipment management software to be developed. We see also in the software stack that you are disaggregating that as well. But when you disaggregate, of course, the challenge is to drive standardization. That's why OCP is a great forum to drive industry standardization, so many people and ecosystem can come together and standardize to drive volume and adoption. So just as a side note, I took that from a recent press release, and it's very impressive how big the open compute industry have become today. So 2.5 billion is excluding Facebook and Microsoft. Think about that. It's getting real industry momentum. And when you have momentum and when you standardize on the hardware side, you commoditize the hardware, which is the whole purpose, of course, of driving open networking and open hardware. So we see the commoditization is coming in on all levels, on the chipset, on the white boxes, and even on the pod level. And here is an example also, the woman from the Linux Foundation, she was talking about some OCP accepted white boxes. This is one example of a white box that we are working with that comes from Acton. And it's their wedge platform. It's an OCP accepted white box. And it has full layer 2 and layer 3 capabilities, and it goes all the way up to 6.4 6.4 terabit today. And you will see also here that in these boxes that we are using a chipset from Barefoot. And why? That gives us data plane flexibility. Again, if you want to bring developers to networking, you need to have flexibility all the way down to the hardware. So how does that box look like from a software perspective? So you see here how we manage that. The data plane is from Barefoot, is P4. So the whole runtime runs P4. Then on top of that, we run RHEL CoreOS. It's a standard Linux operating system. And on top of that, we run a container platform, because every node in the data center fleet that you will see later on is fully containerized internally for us. So we internally containerize the fabric, and then you will see how we also can support an OpenStack, Openshift/Kubernetes integration towards the application side. The benefit here you see also, we use standard bootloader only, and we use a standard support package like OpenBMC. Why? Because then you have a whole industry supporting that. So we use white boxes from many different vendors. And again, if you can standardize on these core software components, it simplifies for everyone. And by the way, if you take one step back and think about what you see here, this is actually exactly the same interface that if you would have a server. And that was the thought when we designed that. So, but in a data center, you have more nodes than just a switch, as we all know. So you see here, application servers, storage servers, the leaf and spine switches, and the fabric controllers. And you see there, our philosophy is that we are leveraging Redfish for the system management. And for the bootloaders, we are using ONI. And on the operating system, we're using CoreOS. And again, one side note to note with CoreOS also is that it's a stripped down version of the operating system. So it takes much less footprint than the standard Linux operating system. So to summarize a little bit on our philosophy versus some other network operating system philosophy is that we believe in using standard Linux. So you see here that you don't have a modified Linux kernel. We use standard ONI bootloader, and you see also other things. When you are using the same CI/CD workflow for the entire fleet in the data center of your servers, your storage node, and your networking, you can use the same CI/CD workflow for all the nodes now. And also, since you use a standard Linux distribution, we can also support SE Linux in a very simple way. So you can add and get free all the security features from that as part of your networking gear. Okay, so moving on a little bit. This is a view that we have put a lot of thoughts into. We want to create virtual slices of the data center. We call that vFabric. And think of that you have a fabric solution managing each individual spine or leaf or controller in the data center. Then on top of that, you can slice the data center even further for different tenants. So you can isolate a few servers or storage nodes with the networking gear and create this virtual slice. So for instance, for people that are data center operators, they can now, instead of doing lift and shift with physical gears, they can equip their data center with the compute, storage, and networking gear and provision new customers in software. So it changes their business model completely. We also seen that the slicing capability, this is a canonical format that can be used for different purposes. So slicing, if you're familiar with 5G, is coming very strong in 5G as a key requirement, which means that you could set different quality service parameter. You can have end-to-end right management. Think of it like an access control list for that slice, which is coupled with a tenant or an enterprise. So the way to think about this is really a layer between the fabric and the top management layer in the data center. So why do you need a programmable data plane? Well, we saw the force on the server and the compute side, the cloud era, the last 10 years. We see when you have a developer-centric design, what that can give. It brings innovation. And we believe that bringing programmability to the data plane in the networking space in the data center will generate a lot of innovation. So what you just saw there before, the virtual data center and the slicing, that can't be done in a fixed function ASIC today. Maybe in a new release in the future, but not today. In-band telemetry, segment routing, different protocol like Geneva and so forth can't be done today. New requirements and new protocols are coming on the whole time. And we believe when you're starting to treat the data center as a whole, from a CI/CD, from a DevOps perspective, that it will put more, let's say, pressure on the networking gear to release more features, to be stay ahead of the curve. So one of those alternatives for programmable data plane is what Barefoot have brought to the market. It's called P4. It's a standard way of programming the data plane, which is independent of the underlying hardware. And we believe very much in that, because then we can get basically a common data plane programming model for the servers, for the FPGAs, for the switches in the data plane. And that also gives portability. So if you design something, for instance, on a server, on an x86 server, you can port that back, for instance, to a Barefoot switch, programmable switch, if you like. So that is a great way to introduce new features. And what you also saw on the previous slides with slicing, when you're running your production network, we can also offer a test slice, which means that you can test new functionality ahead of committing that to the actual network that runs in full operation in production. So we call that network versioning. And we think that's a great combination of adding new programmability and add new features, and in a controlled way introduce those to your production environment. And here we see also, we have also taken a step back and looking a lot on latency sensitive applications. So you see here, from the switch to the servers in the backend, there is a lot of improvement that can be done. So we have introduced something we call Kaloom Virtual Switch, which on average is improving the latency by a factor of 7x. And improves the throughput by 2x. So that improvement, what do I do with that? I can either, do it to get more resources on the server side, because I relax the requirement on what is needed in my servers, or I can take it and have less requirement and give that back fully to the application to benefit that greater reduced latency and throughput. So we believe that's an important factor to think about, to not only think about the switch itself, but think holistically in the data center. And I talked about that our solution is containerized internally. So this is something I get a lot of questions about very often. And so when we think about containerization here, it's twofold. One is internally in our fabric for increased portability and scalability and throughput. And then you have another integration towards the application framework side, where we integrated OpenStack and OpenShift/Kubernetes. So this is the way to think about what, a VNF is now being seen as a CNF. VNF is virtual network function, and CNF is a similar container network function. So they are being split up into data plane piece and a control plane piece. So in this case, since we're using a P4 programmability for the data plane, You see the code in the bottom path here that can go into Barefoot or an FPGA or an x86 server. And then on top there, you see the container network function that is in our Kubernetes application written in Go. And it's a completely distributed control plane for all of our nodes. So, and you will see that in a few slides that, you know, the integration we have in the spine and leaves and controllers, as well as the server backends, are part of the same distributed control plane. So how does a normal data center look like? I mean, we've seen this picture like a million times over the last 2 days. And for us, you see here that you have spine switches and you have leaf switches. So remember the switches you just saw there, the OCP accepted switches, they can be used either as a spine or as a leaf. And the leaf connects to the server ports on the back end, and then you have the spine that connects to different racks of servers. And then you see the same switch can have WAN interfaces and in egress out, either to other pods or other data centers. So, and this is the control plane view. So you see here, remember we have small Linux instances of CoreOS in every node, whether it's the spine, the leaf, or the controllers. And you see here how we treat that as a completely distributed control plane. And this is just another view from our lab. So you see here a typical configuration. You see in the application server racks the leaf switches on top, and you see to the left there the spine switches with the edge switches and the controllers. But remember now, we have a fully distributed control plane. You only use bigger controllers if you have bigger pods and data center. If you have smaller, it's fully integrated in the nodes itself and fully distributed. So it's up to you and the different configuration you're going after. So here is some core fundamental building blocks of our fabric, the way we have designed that. It's a fully autonomous, self-forming and self-discovering fabric. So both the underlay and the virtual environment and the vFabric with the embedded virtual components are fully automated. And we talked about slicing, so we have support for full slicing and can create vFabrics in the fabric. It's fully programmable, and also we do here data plane acceleration. So what we haven't talked so much about is that we integrate, you know, like vRouter, vGateway, virtual load balancer, virtual firewall, all those components are virtual components integrated into our environment. And when we do the offload, think of that like if you have a router that we integrate the fib part in our fabric, and the rib part is part of this distributed control plane. By integrating it that way, we offload and increase the performance, and it enables very simple service chaining. You can support segment routing, if you like, and stuff like that. And of course, we support multiple white boxes from Acton, Delta, and many others. So this is a little bit more detailed view of our architecture. So you see there in the controllers, the green pieces there is the centralized control functions running Openshift. So it's a container network function internally. And then you see on the leaf and spine, we have the distributed control functions with the embedded container network functions as well. And then towards the application side, you see that we have integration here towards OpenStack via standard ML2 plugin. And we have integration with OpenShift and Kubernetes over the CNI interfaces. And with the CNI interfaces, like I said, for people that are interested, we are doing a lot of work in contributing to Kubernetes and Linux Foundation. We have improved a lot of the CNIs in terms of mission-critical application. Today, it supports one interface, and if that changed, you need to turn down your application. So we added, there was a framework called Maltus, which added multiple interfaces, and we have made that so it can be dynamically changed in runtime. Why? Because you can get network changes in the data center So, and we talked to many customers that were developing an application and they couldn't figure out why they need to tear down their Kubernetes-based application. That was due to this reason. So again, you need to have a holistic view to the whole data center and how you improve the application performance.
Thomas, time check, you got about 1 minute.
1 minute. Then I show this page. So like I said, I talked a lot about open source standardization. So people that are interested, please reach out to me or other people at Kaloom. And here you have some GitHub links with the Kubernetes improvement we have done. KVS, remember, that's the I/O. Think of it like an DPDK improvement between the I/O and from the switch to the server. So people that are interested in that, we're happy to share our thought process and what we have done there. I think I stopped there.
Okay. All right, thank you. We have time for maybe one question. If anybody would like to ask a question, please use these 2 standing mics. Yeah, come up here. Yeah, we're...
Somebody else with a question. I was like, well, they can go first. I just want to understand, there's no dependency on Barefoot to this architecture, and there's no requirement to have to program the data path, right? All of this value can be applied to any switch, or is that a correct assumption? Thank you.
First of all, a programmable switch can deliver this, yes. But not all of this innovation can be done on a non-programmable switch. So for instance, like the slicing in a virtual fabric can't be done on a Broadcom, to be specific. So there are some devils in the detail here.
Okay, so Broadcom does have programmable products also. So you have to have the data path too. So the data path has to be programmable for this to work? Or
No. You can have a fixed function ASIC like a Broadcom non-programmable for it to work. You can have a Mellanox. And we can have other programmable switches. It's just that some of these features you can't deliver on a non-programmable switch. There are new innovations. That's the challenge.
Sure. So that's great. I wanted to clarify that. That's valuable.
Yeah, thanks for bringing it up.
Okay, thank you, Thomas.
Thanks.